Okay, so we are going to talk today about how we use indefinite integrals to solve specific kind of applied problems that you're going to have. The main concept that we want to know is that if you have a function f of x, its derivative is going to tell you the slope of that graph. Now, that is a derivative, so that's d over dx. Now, if we go backwards, let's say we have a function. Let's say we have a function that says this is the slope of something else. Well, we would then use the indefinite integral function to move backwards. Now, the one thing, though, is that we have this thing called a plus c. And I'll explain that concept here in a second. So let's say we have a function. Let's say our derivative is just the function equaling 2. So we say that our slope is always 2. So the slope of our graph is always going to be 2. Well, that tells us lots of things. So let's see here. So excuse me. So f prime of x equals 2. Well, if you integrated that function, you would get this answer, 2x plus c. Okay, so that is a line with a slope of 2. Now, we don't know what this plus c is, because look at this. I could have a function with a slope of 2 going through the origin. That works. But I could also have this function, or this function, or this function, or this function, and so on and so forth. It's so long is that it's actually the same graph. The only difference is your y-intercept. So here, here, obviously this is not drawn perfectly to scale, but hopefully you get the idea here that this, as long as it's the same function, just a different y-intercept, so the same slope, then it works. Now we don't know which one it is necessarily, and that's where we need a little bit of extra information. But we can always find a graph or a function, some sort, even if it's general being this plus c form, that'll tell us what our higher function is going to be. Now, if we have a little bit more information, we can actually find what that function is. So, for example, let's say they gave us that this is true, and then also that, let's say they say f of 1 is 4. Okay, so let's say they say that this is true. Okay, well, when we do our integral function, so when we integrate f of x, we got 2x plus c. Okay, so excuse me, when we integrate f prime of x, we got 2x plus c. Well, now what we do is we say, okay, well, if this is also true, f of 1 is going to be 2 times 1 plus c. And so therefore we know what our c value is. We know now that f of x is going to be 2x plus what number? No longer c. We know that it's going to have to be 2, because in order to make these two equations work together, c would have to be 2. So we know that with these two pieces of information, we can find specifically that my function is going to be 2x plus 2, which is going to look something like this, right? We know that that's going to work. Now, again, it could be any function unless we have this extra piece of information to help us out. Now, this can be extended even further if we know, like, let's say we have our second derivative. Let's say, for example, our second derivative is 2. Well, that means that our first derivative, if we were to integrate, our first derivative is going to be 2x plus c. So the same idea. So we don't know necessarily what's going on there. Well, in order to, if we were to integrate this, to try to find what f of x is, we end up with something very interesting. If we integrated this function here, 2x, the integral of 2x is going to be x squared. Well, what's the integral of cx? Okay, c just being some number, or c, sorry, is going to be cx. Because remember, we have to add 1 to the exponent of x, which for a constant, the exponent is 0, so it becomes x to the first. And that's what we get. Now, we have to add on another constant because we don't know what it is. So you might see this thing called plus d. It's just an extra letter saying that it could be any type of function. So the main thing is, if you're given a second derivative, you can find exactly what you need, but you now need multiple pieces of information. Okay? You would need to say, like, okay, so like in the last example, we said we knew that, let's say, f prime of 1 is 4. So we used that and we said, okay, well, c is what? 2. We knew that from the last problem. So we knew that f prime of x was 2x plus 2. So when we move up again, and we say f of x, and we try to integrate that, we know that this is x squared. We know that our cx now, because we know c is 2x. So we need one more piece of information to figure out what the d value is, what the extra constant is in order to make this work. So as you integrate, every time you integrate, you have a constant that you are adding. And you need a piece of information to tell you what that is. Now, all of this goes back to slope. And you'll also see, slope, that means the same thing as gradient. So if you see that as an answer, gradient, if you see this word, it means slope. So that's what we're working with right now. We're talking about slope as far as being values of certain functions, and when we integrate, that's where we're finding functions with these particular types of slope.